Our current understanding of the universe and all the matter within it is captured by these two images. The one on the left is the standard model of particle physics, which says that when we look closely, all matter is made up of just a handful of subatomic particles, bouncing off each other in various different ways. The one on the right represents our understanding of the entire universe, and it says that all of space is expanding like a balloon, and that this expansion started at a single point in space and time 13.8 billion years ago, which we call the Big Bang. Now, although this model has been extremely successful in understanding the world around us, it's not the entire picture, and there are some gaps that need filling in.
For one, the standard model says that every matter particle has a partner called an antiparticle, which looks almost the same, but with all of its properties flipped in the mirror. For example, the electron, which has a negative charge, has a positively charged partner called the positron. The standard model doesn't say that either matter or antimatter should dominate over the other. So why did the Big Bang produce mostly matter? This is called the baryon asymmetry problem, and researchers in Manchester are studying a process called CP violation in the hope of finding an answer.
For matter to dominate over antimatter, there needs to be processes which can favour one over the other. Such processes would violate a symmetry known as CP symmetry. Under the symmetry, you can imagine taking all the particles in the universe, replacing them with antiparticles, and then looking at the universe through an imaginary big mirror. If, under these conditions, you get the same laws of physics, then the symmetry is respected. Instead, if the laws of nature are different in this case, then you can get the difference that you need to produce more matter over antimatter. And this is what we believe is happening.
Now, until recently, CP violation had never been detected for particles called baryons, which is really a group of particles that includes the more familiar proton and neutron. To understand how these particles behave, we smash protons together at nearly the speed of light, using machines like the Large Hadron Collider, or the LHC for short. Then by studying these collisions, we can search for signs of new physics, like CP violation.
At the LHC, we collide protons in order to understand the particles that arise from these collisions. One of the 4 large experiments of the LHC is LHCb, Large Hadron Collider Beauty Experiment, whose main area of data analysis is to understand the differences between matter and antimatter particles. Right next to me, you can see one of the sub-detectors of the LHCb, which was actually built in this clean room at the University of Manchester, the so-called vertex locator. What we can see here is one module, and you can see the sensors that we're able to detect the particles that go through it. With this high-precision technology, we were able to find 18 new particles within the last year, and also to find evidence of CP violation in baryons, for example. You can consider as LHCb acting as a magnifying glass towards finding new physics, finding new particles, and really discovering the nature of our universe.